All right, so if we look at the problem of the day, I was asking you guys to identify whether or not the reaction was going to be SN1, SN2, E1, or E2. If we look at the first problem, we've got a secondary alcohol, we've got catalytic acid, and we've got heat. What does this scream out?
E1.
E1. So E1 reactions, just like we saw in our cyclohexanol lab, are favored whenever you have a secondary alcohol, acid, and heat. And in this case, there are two potential products you could get. One product would be this guy, and the other one would be this guy. Now the question is, which one would be major and why?
The second, because the electrons are further apart.
Yeah, this is tricky and it's not super intuitive. We haven't actually gotten this far yet in the Klein textbook. But one thing you'll notice about the alkene on the left is that we've got an sp2 carbon here, sp2 carbon here, sp2 carbon here, and sp2 carbon here. Those electrons really like to be able to delocalize across adjacent p orbitals, which actually makes that alkene the major product and the one on the right minor. So just for fun, I'll label these. You don't have to. And what we call these alternating double, single, double bonds, we call them conjugated. The one on the right would be isolated double bonds. Double bonds really prefer to be conjugated if there's an option to. All right, problem 2. If we're looking at problem 2, we've got cyanide, so Cn minus. It's a pretty weak base. I know some people were Googling it and it said it was a good base. It's really not a good base. In fact, we don't want it to grab a proton. Does anybody know why? Yeah, it'll make HCN, which smells like almonds and will kill you. So we preferably don't want this to do acid-base chemistry. We only want the nucleophilic attack. Is this going to do SN1 or SN2? SN2. SN2. If you remember the other day in class, I said secondary carbons can do SN1 or SN2. Why would this one do SN2? Yeah, we've got a polar aprotic solvent and we've got a good nucleophile. So in this case, SN2 would be the favored product. And we have to invert that stereocenter. So in this case, you notice how I changed that hydrogen from a dash to a wedge, and I changed the methyl group from a wedge to a dash. That shows that inversion of stereochemistry.
I get the inversion, but I just did it on the same sides as they were, so I put a dash.
Yeah, the main thing I would look at with this one is I would look for your product to have a specific conformation. So in this case, this would be priority 1, priority 2, priority 3. So would this be R or S? R. So regardless of how you draw it, I mean, you could draw it upside down, flipped around 4 times. It doesn't matter. I would just check to make sure you drew the R product. All right, the next one. We've got sodium hydroxide, and we've got an electrophile that's on a secondary carbon. So would this favor E2, SN2, SN1, or E1? Yeah, it would primarily favor E2. We might get a little bit of SN2, so I'll just put a dashed circle around that. And in this case, there's a variety of different products we can get. We've got 2 beta protons here and here. So we might get our trans double bond there. Or we might get our cis product there. So those are 2 potential products between that alpha and beta position. And then we also have another set of beta protons here and here. So let me actually slide this over a bit. Oops. So we've got those 2. And then if we grab the other set of beta protons, we would end up with the double bond on the next carbon over. Or we could end up with the cis product as well. All right, so we end up with 4 different E2 products. And then if you really want to be thorough, you could draw that minor SN2 product. So I'm going to shrink these down a little bit. Whoop, shoot. That didn't work. There we go. And our minor product might look something like this. Some people were asking me about this bromine, and they said, well, you didn't draw it as a dash or a wedge. Does that mean it's not a stereocenter? Not quite. It just means that the starting material I have shown is racemic. It could be R or S. I'm not implying that it's specifically one enantiomer or the other, which means that your SN2 product would also be racemic because we don't know which starting material we're dealing with. So that was a good question for those of you that were asking about it. The next one, we've got sodium ethoxide, and we've got heat and a secondary electrophile that's particularly hindered because of those two methyl groups. So what pathway would this favor? SN1, SN2, E1, or E2?
It's E2
E2? Why do you guys think it's E2?
because of the NaOE2.
Yeah, so it's a good base. It's also a good nucleophile, but why is it probably not going to do an SN2? It's pretty hindered to get to that backside. It's not only a secondary carbon, but we've got two adjacent methyl groups that are kind of blocking it from doing that SN2 attack. So if you did draw SN2, yeah, I mean, you could argue that maybe you get a trace amount of SN2, but primarily this is going to give you an E2 product. The heat is the other indication that it's primarily going to favor E2. So we could get this product. What about this product? No? Texas carbon. You'd make me sad if you drew that. So don't draw Texas carbons. We should be out of that phase of our lives by now. Let's go to the bottom one. Does this look like a good leaving group? Yeah, it looks like a good leaving group. We've got a tertiary carbon, and we've got a weak nucleophile, weak base. What does this typically favor?
Mix of SN1 and E1.
Yeah, mix of SN1 and E1. I didn't give you heat, so you really can't say it's going to favor elimination over substitution. It's just going to end up in a mixture. So if we draw this, we could say, all right, we could end up with our substitution product. And is that the only substitution product that we'll get? No, we could end up with its enantiomer as well because we're going through a trigonal planar carbocation. Yep.
So for that question, you circled two, both SN1 and E1, and I understand why you did it, but your instruction on the paper says to circle only one.
It's fine. I'll just have to take a look at what you have on the paper. But remember, SN1 and E1 is oftentimes uncontrollable, and you end up with a mixture of products out of it.
Because I wrote both of it, I just didn't necessarily put everything in one.
Okay, that's fine. I'll try to figure out what you wrote down. All right, so if we look at the elimination products, we've got a handful of them. So we've got beta protons here and here. So we could end up with a double bond forming between these two carbons. So let's draw that. So we've got an isopropyl group and we've got a methyl group. Could we end up with any other product from those beta protons?
That could be cis.
Yeah, it could be cis. Right now I've drawn trans. So we could end up with our cis product, which would look like that. So that's one set of E1 products. We also have a beta proton out here. So we could end up with our double bond that looks like that. Or we've got beta protons out here. So you could end up with something that looks like this.
So if we didn't draw every possible one, but we drew one right one, we still get the
Gosh. I have to take a look at what's on your paper. But the important thing to remember is a lot of books or online sources will teach you it's got to be SN1 or it's got to be E1. It's not always cut and dry like this. Oftentimes you end up with this hodgepodge mixture of reaction products out of this. Out of all of these alkenes, which one do you think is going to be the favored alkene? First, second, or third? Third. So this would be our major E1 product. Why is this one going to be our major E1 product? It's tetrasubstituted. Yeah.
So why are they cis, 30 cis, when you're just moving hydrogen atoms?
So are you referring to these two and asking why are
No, the three.
with this one?
Yeah, all of them. They're cis, but not trans.
So for that third one, could we really label that third alkene as cis or trans? No, we can't label it as cis or trans, so that's the only product we get out for that one. All right, so what I did last night was I cleaned up the in-class activity from yesterday, and I would really recommend using this as a study guide for not only this upcoming quiz, but for the final. And if you go through and look at this, there were a few tricky ones. For example, the one on the bottom, I made a little note that sometimes it's not super clear that it's going to be SN2 or E2. In this case, it's a primary carbon. We've got a strong nucleophile, strong base. The flowchart or the scheme we went over in class said it should favor SN2. But if we think about the nucleophile doing the backside attack, it's got to get past that cyclohexane ring that's dangling off. So in this case, it might actually favor E2 products. And then, if you go through to the last three, they are a little trickier. These are E2 reactions primarily, and in this case, these are reactions where we have to consider the Newman projection or the chair conformations for these. So these are good ones to practice with in terms of drawing out the full mechanism. Today, what I have for you guys is another practice worksheet. The reason I'm doing 2 days of practice was, to be perfectly honest, my students last year struggled with these, and I want to make sure we get these down and nailed. So we spent a lot more time on these. What I am going to ask of you guys today is to get volunteers to draw out the complete mechanism on the board. So I want you guys to help me with the complete mechanism and then explain your answer to the class. So if you guys can, get in a group of like 3 or 4 people and try to come up with mechanisms for each of these, not just the products.